Welcome to this course. This is on biomedical imaging system at an introduction level, so titled as Introduction to Biomedical Imaging Systems. Myself, Arun Kumar Tittai, I'll be handling this course, and this is essentially tailored towards biomedical engineering students if you are in a curriculum. Typically it is a 7th semester, 8th semester course, or postgraduate students. This will be your first year regular core course. So of course this is also open to other students from different backgrounds, and no real prerequisite is assumed beyond basic introductory linear algebra and physics, and which is typically taught at first year. This is the rough course plan that we will do. So what you see here is planned for, it's typically 12 to 14 weeks. Given the format, we will try to cover for 12 weeks, and we will try to cover different modalities in a specific manner. For example, you see the reference books here. As you will notice, this is kind of taught well with or traditionally taught as an imaging physics course. So you see some of the classic textbooks like Makowski, which are basically of physics of medical imaging. So recently we have a lot more engineering students start to take this in biomedical engineering program in the last maybe a decade or a couple of decades. So there is going to be some physics but also engineering aspects to it, and so the title of the course is also appropriately named as Imaging Systems. So what we will try to do is cover all this. Each of them are self-contained. Each modality is self-contained. It is organized such that you could in fact start with introduction, do the basic, and then jump to a modality of your choice. Maybe that is the one that you are going to work, that is the one that you got job for. So you could actually without losing the generality, you could jump to a particular modality and start to cover that from the physics and the engineering perspective. And these are the reference textbooks. Like I say, it is reference because several topics are good in certain textbooks. So some material will be taken from one text, others from others. So what we will try to do is, I will try to keep a format that is consistent with the first textbook here. This is in view of the fact that this textbook is also available in India as a Eastern Economy edition, so you could afford the textbook, and so it's available. And so that is the kernel, that is the theme that we'll start to use, but we will take certain portions from the other textbooks as well. Okay, so moving on, before we actually jump into the subject itself, let's just take a big picture view where this topic or where this subject is going to be listed, right? And you will see that we have electrical engineering, civil, mechanical, computer science, and you will not see biomedical engineering. So this is not listed as a vertical. But this is one of those subjects which fall in the multidisciplinary or interdisciplinary programs. And in some engineering colleges, globally if you look at it, some fall, these biomedical engineering itself falls under a vertical of complex systems engineering. Okay, so there are several ways to look at it, but essentially this is the theme. All of it is going to deal with something to do with anatomy or physiology. Our idea is to get some information from the anatomy or physiology. So that is what the whole biomedical engineering is dealing with. Given this broad theme, since there is no core program globally, in the last 2-3 decades, each country, each continent, depending on their availability, each schools, they have kind of taken a strong hold, and we could broadly classify them with the different verticals. For example, what you see here, you see a lot of devices, right? This is a hospital, you have a lot of instruments. So those could be taught as one particular subdivision, right? Or here you see a signal, right? This is a typical ECG example that you see. So this is a signal. So you also see some implants right, which have, so these are to do with material properties. And one of the earliest understanding is to do with skeletal motion, so your biomechanics. So what I tried to list here is the branches, if you want to see, the clusters of work that is grouped worldwide depending on the availability or access or the expertise to a certain aspect of biomedical engineering can be grouped as biomechanics, instruments, devices, biomaterials. Of course, I have only signal here, which is called biosignal processing, and deliberately I left it there because I didn't talk about this one another big vertical. So as you can imagine already, typically this is covered in a electrical engineering course. So students from electrical engineering background may have a lot of prerequisites or base core material taught in their electrical engineering program curriculum. This comes from mechanical engineering background, mechanics will be taught. So biomechanics, typically students from mechanical background find it a lot more interesting and feel connected to. You have biomaterials, right? Likewise, biosignal processing. I just deliberately left signal processing, but you would also now be very familiar with image processing. So biosignal and image processing. So most of these groups mostly come from electrical engineering school. So as you can see, why I highlighted medical imaging separately is, this is a mix of all different backgrounds. So this is actually in some sense interdisciplinary within the multidisciplinary biomedical engineering program. So we'll just focus one more slide on the big picture. So what is medical imaging, right? So the moment we talk about medical imaging, what comes to our mind? We are all very familiar. We have encountered this. Immediately we'll say, I know my father was asked to go for a echocardiography, right? I was asked to go for an abdomen scan. My brother went for a chest X-ray. So we kind of use it, but you notice carefully all this language, there is no hierarchy. Some are saying that they went for a head scan, abdomen scan. In some place you say they went for an MRI. Some place you say they went for chest X-ray or an angio. So you really look at it, you are either talking about a modality, right? Or you are talking about the application where the problem is, the organ that is being investigated. So there is no big, when you use it, the way you would have probably formed your opinion about a topic, it is still scattered, right? So the objective is, actually there is a very nice, beautiful organization, built up on these topics. So for example, if you say brain imaging, if you want to characterize all this based on the application, right? Then you see immediately within that, if it is just going to be brain imaging, you could end up taking the brain image using different modalities. Some of them are listed here. Say you would have been familiar with MRI, right? X-ray, this is PET scan, which is basically positron emission tomography, right? We will cover that. Then you have your CT, which is computed tomography. So you could immediately organize, when you talk about imaging, you could take a standpoint from a clinical perspective. So this course, you will find umpteen textbooks in medical imaging from a clinical perspective, okay? Because they want to know what is normal, what is abnormal, and then go for the diagnosis. So that is one way of grouping the topic. Other way is, okay, this is fine. Our interest is not on the clinical application. We are not going to use these images to do any diagnosis. Our objective is, if I see this image, do I know where this image is coming from? When we say we know where the image is coming from, it has to come from instrumentation. So again, you would have been very familiar with CT scan or MRI. So you can see the instrument is also very complicated, and typically you use one of these instruments to acquire these images and acquire data and reconstruct these images. And in typical biomedical instrumentation course, right, we really do not cover instrumentation for imaging systems because this is a whole breed by itself. So in this course, right, when we talk about biomedical imaging system, we are going to talk about some of these modalities and how these images are coming using the instrumentation of the corresponding modality, right. Some can be as complex, and you also have few others. Probably some of you may be able to recognize this. You would have been gone to a doctor, you will say, I know that. That is your ultrasonography machine. So it has its own advantages, right? Non-ionizing, real time. So unlike CT or MRI, where you are asked to lie inside the patient bed and you basically have to sleep, and then they do the imaging and they give you a disk of images after you come out or share it with your doctor. Ultrasound, you could actually lie down and you could see your own image. I mean, not that you will understand anything, but at least it is real time and it can be moved around. Okay, so this is the broad contours of medical imaging. So you have different aspects. Why I said of different background people can be interested. They can come through and attend some of these modules is because of this reason. So what we will attempt to do in this course is, this is the learning objectives. What I mean is, okay, you end up taking this, you listen through the videos, you in fact go through one of the modules, one of the imaging modalities. You should be able to at least explain the basic principles. Of course, if you take one of the module, at least that particular module, you should be able to explain what it is. When I say explain, now is the trick. We are not doing clinical diagnosis. That means we should be able to explain when I see a green pixel or a yellow pixel or a grey pixel or a black pixel, do I know what it means? Do I know what it represents of the body? Do I know how we got the pixel there? Why is the value so much, right? So that is the aspect that I would expect. To some extent, you be able to analyze the system. When I say analyze, it is not analyzing the image. It is analyzing the system. What do we mean by analyzing the system? Is the image showing poor quality, right? Is there a dropout? Is it because the patient himself biologically does not have the signal there, or is it because the instrument probe is gone, or is it because of software, right? Any of that. So you should be able to analyze the output and understand the system and system settings that give rise to image. This is very important, I say, because most applications people, I find some of our students tell us they get image processing job, right? So they go do some MRI brain image processing. But the challenge is when the doctor is asking, why am I getting this image artifact since yesterday? It's not because the patient is different suddenly. It is because one of the subsystems, there is some miscalibration, there could be some element that has gone. So this engineer who is going to help them should actually have the ability to understand which subsystem could possibly cause the error, so that they can then call the company and have them come and change a component. It could be as simple as that, or maybe this has had its life, you change the whole system. Okay, so that is something that I typically encounter from our students when they go for a job and they ask, oh, I applied this filter, I get this image, but the doctor is saying there is some problem, So I think that is important. This is a key thing. This is the challenge. Each modality, you should know what is the weakness and also its advantages. This is important because as a student, when you take this course, typically what happens is you look at industry, you look at your seniors, you ask them, and they say, you know what, now for example, what I encountered when I was a student, you're working in ultrasound, MRI is the next breadwinner, because when I was a graduate student, two Nobel Prizes were given for MRI. So they said, MRI is going to eat up everything, there is no scope for ultrasound. But in reality, the more you start to understand and more you can reason out, I think each modality has its strength and weakness. So you should be able to clearly articulate, understand that, so that it is not only good to you, because you will become comfortable in making your choice, but also to the person whom you are advising, right? So a doctor could be there, he will say, oh, you know what, they released a latest scanner last month, and they are saying this gives superb image quality. As an engineer on board, you should be able to say, well, these are the specification here, these are probably cosmetic, it's just marketing language, there is no fundamental change in the quality, so this is a price that we can afford, this is an investment that we can make, or no, this is just something that we could do it in-house as well on our existing scanner. So unless you are clear about these and you are able to work in a team and explain to the doctor, right, that is a skill set that is really needed. And therefore one of the objectives of this course, the way it is tailored and the way I will try to give examples and homework problems and assignments, is keeping in view this aspect of engineering, because there are several classic textbooks on the imaging physics, the old subject. But when you try to apply that knowledge to the current technology with the end user in perspective, I think that is a gap that needs to be addressed, which this course will strive to address. So we will actually stop here and then start with modality specific introduction in the ongoing lectures. Thank you.